In this video, we're going to formalize our idea of finding the slope at one point on a graph, and we're going to define that as the derivative of the function at a point. There's going to be a variety of different notations that are used for this, but they all mean the same thing, and they're all simple scalings or shiftings of the same basic premise. The version that we've seen before was this one here, where we pick a point on the graph. That's our point C. That's an x-coordinate. And we also pick a point that's just a little bit further, delta x across, and that gives us a new point, C plus delta x. We then find the rise over the run, so the value difference between the function values at the end point and the start point, divided by the interval width, delta x, and then we let that delta x get smaller and smaller. We anchor ourselves to the one point, and then we move that second point closer and closer and closer, and that gives us closer and closer approximations to the tangent line slope. In textbooks, you'll typically see the notation up here where the more generic letter h is used, but h is exactly the same thing as delta x. So we have our point C, and instead of going across by delta x, we use this sort of anonymous value h, but otherwise it's all the same rise over run calculations. A third way is to look at it as two separate points. So one is the point C and the other one is the point X. And again, if we find the rise over run and that connection there, the only change or how this looks different is instead of thinking of the interval as being what's changing, we think of this X being moved closer and closer. We see that in the limit formulation here, that we're going to push that second point closer and closer to the first point. In the earlier examples, we said the difference between the 2 points is going to get closer and closer to 0. They mean exactly the same thing in practice, though. And the difference in the denominator here is based on the run, which is literally the distance between those 2 points. So all of these formulations you may see in different scenarios, in different environments, different textbooks. They're all the same thing under the hood. If you draw the picture of all three of these scenarios, you get the same picture. It's just a question of how you define the variables. All of these also mean the derivative of the function f at a point C. As an example, we're going to find the slope of the function y equals x squared, so a parabola, at the point x equals 2. And we can again sketch this. We should be able to approximate that slope and say, well, it might be around a run of 1 and a rise of 3-ish maybe, so maybe 3, but we don't know. We could be a lot more precise if we go back and we use these definitions. Now, some of you have already seen formula approaches to this. You might be thinking 2x in the back of your mind. We're getting there. That's next unit. But for now, we're going to rely on the fundamentals. We are going to say that the derivative of f of x at the point x equals 2, is our point in the question, is going to be defined as the limit as, let's take the delta x goes to 0 version, and we're going to look at the function value f of x plus delta x. So a little bit to the right first, minus f of x, and all over delta x. Now I can be a little more precise here. We want to evaluate this at the point 2. So 2 is what our anchor point is. And again, what we can do is note that our point 2 is one element of our sketch here. Then we're going to take a point on the graph somewhere else, and it's going to be delta x further along, and the value we get here is the value at 2 plus delta x as our input, and we want to know the output at that coordinate. And so if we want the rise, we're going to take the difference between these two values. If we want the run, it's simply this point minus that point, which is delta x. Well, now we can use the value of our function, which is f of x equals x squared. So we're going to ask, what is the slope approach when delta x gets smaller? But we can be more precise in our calculations. We can actually use the x squared formula and say this is our input, so we square all that. For this function value, 2 is our input, we square all of that, and we have delta x in the bottom. It's worth noting that even at this stage now, if we try to sub in, we're going to have the problem that we have with every derivative initially, that we're going to get in the denominator a 0. We're going to have delta x getting smaller and smaller and smaller because that's the limit we're taking. But fortunately on the top, we actually end up at 2 plus 0 squared minus 2 squared, and that is 0 over 0. We know the value doesn't exist at 0, but we don't know whether the limit exists because this form is one of those indeterminate forms, which again means that we need to do more work first. And by more work first, we mean simplify and see if we can rewrite this formula in a way that this limit doesn't turn out to be indeterminate. So let's go and do that work. Take the limit as x approaches 0. What we can do here is expand this expression. It's a square, so we'll have 2 squared plus 2 times 2 delta x's. Remember, squaring a polynomial like this, we get 2 times the product of the two other terms, and we'll have delta x squared as well. And that doesn't change the denominator at all. However, we do get to tidy some things up here. In particular, we have 4 minus 4. Those will cancel. And that'll leave us with 4 delta x plus delta x squared all over delta x. And here, because delta x is not exactly 0, we can cancel it as we need to in the top and bottom. And the safest way to do that is to factor 1 out of the numerator. If we notice that every term in the numerator has a delta x, we get this relationship here, delta x times 4, 4 delta x times delta x squared, and now we can do that cancellation. After we've done the cancellation, we can do the subbing in to evaluate our limit, delta x approaching 0. Oh, there we get 4 plus 0. And so we should see that the slope of a tangent line at the point x equals 2 is actually 4. This is strictly using the definition, what we mean of rise over runs, when the run distance gets smaller and smaller and smaller. Here's a more detailed view of the graph of x squared around x equals 2, and what we should be able to do then is see that the slope of the tangent line, which is what the derivative means, is exactly equal to a slope of 4. Now if we're careful with the units on the axes here, here is a run of 1, and we're at 4. If I want a slope of 4, I would go up 4 to 8. And if we draw the connection line here, it should look like a tangent line. And if we repeat the same thing on the left-hand side as well, there, we can see that this line is as close to tangent as we can get with an eyeball inspection, so it reinforces that the calculation we did in the last page is correct. This is the graph of a tangent line, and its slope is exactly 4, and that matches the slope of the function y equals x squared. We're going to move on after this and formalize the notation for the derivative and how we can calculate it a little more easily and quickly than using the definition. We don't always want to come back to this if there are easier ways to get to the same result, but this is underpinning everything else that we do as we move forward in the course. This is going to be our definition of the derivative, extending the simple rise over run formula to very, very tiny intervals or single points.